Good morning, everyone. Last time we talked about the electric force, and then today we're going to talk about electric field. And then last time I give you the comparison with the electric force with the gravitational force. Again, gravitational force is a G times M1, M2 divided by R square. And then electrical force, based on Coulomb's law, is K times Q1, Q2 divided by R squared, right? And then the physical meaning of the gravitational force is a force between two objects with masses. Electrical force is a force between two charges, right? With non-zero charges, right? And then, one example of this gravitational force is a force between you and the Earth, which is a weight, right? So for example, you have a Earth here, and then Earth's mass is me, and then your mass is a small m. So then your gravitational force, which is weight, is simply what? Me m divided by re square, where r is the radius of the Earth, right? And then of course you have a g here, right? And then these three combination is called gravity G, right? But now think about the physical meaning of G here. G is independent of your mass. It's a G, gravity, G, small g here, is a function of a mass of the Earth and the radius of the Earth, right? So this is nothing about, the mass, your mass here, for example, here, right? And then we define same quantity for electric force, independent of the second charge. So this combination is called electric field. So in other words, this is electric field times a Q, oops, sorry, Q2, right? Again, the concept of electric field here is electric field is independent of the second charge. Like a gravity is independent of the second mass, right? So your gravity is assuming instead of yourself, we place a mass, a small ball whose mass is a mv. And then you simply, in order to find the fg, you simply replace this m with the mv, right? So you can basically have any mass here, which is independent of the g. So in other words, g is kind of a field emitted by the Earth, right? So that means you can also assume this electric force is between two charges, right? So in general, we call first charge Q1, Q source. And then we call second charge Q2 as a Q test. And then this source charge emit its own field. It's kind of due to its charge. So it's called electric field. Again, electric field is originate from QS. It's independent of a Q test. Okay. So then now you can also say electric field, which is a vector, is Q divided by Q. Sorry, F divided by Q. So that means your F again is a electric field times a test charge Q. So your E will be F divided by Q test. So this Q is a Q test charge, right? And the unit for the electric field is, of course, force divided by charge. So Newton divided by Coulomb, right? And then, in other words, this is exactly what I explained. You can use charge Q as a probe to determine whether an electric field is present at that point in space. So this is kind of a Q test, right? If a charge Q experiences an electric force at that point, then there is an electric field at that point causing the force. Of course, right? This is exactly what I explained here. If you have a source charge emitting electric field, So then because of this source charge, at some point, there's non-zero electric field. And then if you bring your Q test here, and then this Q test will feel force due to the electric field. So you can either interpret electric force in terms of interaction between two charges, or you can also assume electric force is based on interaction between electric field by source charge and times the new charge. And then, so for example, instead of us saying here, this is the point that you are interested in, and then if there is electric field E1, if there's electric field E2, that means that there's somewhere in this space the source charge exists. Okay? So in the field model, the field is an agent that exerts an electric force on a particle with a charge Q, right? So electric field, again, is a vector. It exists at every point in space. And then if the probe charge Q, I'll call this is a test charge, is a positive, the electric field vector points in the same direction. Okay, and again, most importantly, the electric field is independent of the charge Q. Again, this is your test charge used to prove a field. The electric field depends only on the source charge that create the field, the electric field, right? And a point source charge Q create an electric field in all direction. And then we use the second charge Q prime, which is test charge, to test the electric field. If both charges are positive, again, the force is given by Coulomb's law again, and the direction again you determine based on sign of this, right? So the concept is exactly the same as what we did for the Coulomb's law, right? And then of course electric field formula is a K Q. This Q is a Q source, right? Divided by R squared. Remember why this is Q source? Because of your F electric force is a Q source, Q test. Of course, you have a K in front and then R squared. And this combination is your electric field. Right? Again, so your electric field is a K times Q R squared. So we use the absolute value here because we not care this time, the sign of it because we are interested in magnitude only. But if you are interested in the magnitude, if it's a positive charge, then it's away from the Q. If it's a negative charge, it will be toward the Q. I will give you some pictures for this. But for now, let's focus on the magnitude of a KQ over R squared. So an electron in a hydrogen atom orbits the probe at a radius of 0.053 nanometer. What is the electric field due to the proton at the position of the electron? So now you have think about the structure of a hydrogen atom. You have a proton at the center whose charge is 1.6 times 10 to negative 9 coulomb. And then 0.035 nanometer away, you have an electron whose charge is the same amount. And then what is the electric field? Again, distance is 5.3 times 10 to minus 11, because this is the nanometer. So this is the distance R squared. And the K again is 99 times a charge. So this is going to be the electric field due to the proton. Okay? And then electric field at a point charge, again, if you have a proton positive charges, electric field is outwards. So the field vector points away from positive charges. Right? So this is the electric field diagram for a proton or a positive point charge. So it's all vectors point straight away from the positive charges. And then if you have a negative charge or electron, field is toward the electron. Okay, this is opposite with the proton, and this is a electron. Okay. And then you can draw the electric field diagram. So diagram is just representative sample of electric field vectors, right? The field exists at or in other point, right? A well-known diagram gives a good indication about the electric field. So again, electric field is a vector, so you again need two parts, right? So the arrow indicates a direction, and the strength of the electric field at the point to which is attached. At the point where the tail of the vector is placed. The length of any vector, as you know, is significant because this is a magnitude, right? And then this is also relative to the lengths of other vectors. I'll give you, and then for the next one, although we have a draw vector across the page, from one point to other point, electric field vector does not stretch, right? From one point to the other point. Okay, I will give you what this mean in a few minutes. Okay, and then let's solve this question first. What is the electric field at point A and the point B? So electric field direction is based on this arrow. And then how can you find the field strength? Field strength is proportional to density of your field line in that area. For example, area A, you have about 2 or 3 lines, right? If I draw additional lines here, right? So this is a kind of a density, which is a strength of the electric field in that area. But if you draw the same size of the circle, you will see there's only one field lines. Right? Maybe you have another line here, but you see the density here is lower than density here. So you can say point A has a stronger electric field. So order the lane, rank in order, largest to smallest, the magnitude of electric field at the black dot. Again, your electric field is gonna be K times a Q source charge divided by R squared. So this is exactly electric field over E1, right? Number one case, right? Charge is Q, and then distance is R. Second one, E2, it's gonna be what? K times Q now, so you increase your charge 2 times. And then distance is also 2 times, so basically this is a 2R squared. So then if you take the numbers only, so you have a 4 denominator and 2, so basically this is 1/2 times KQ over R squared, so which is a half over E1, right? And the third one, you see E3, same except you have a 2Q and still R squared, so this is a 2 times E1, right? And the last one is again K, Q. Now you have a 2R only. So this is a 1 over 4 E1, right? So the answer is D, where C is the number 3 is the strongest, right? And then this 4 is the lowest, right? So the answer is D. And then 1, 2, if you compare 1 and 2, 1 is a greater. So 3, 1, 2, 4. The similar question, all charges shown have equal magnitude, right? So for cases number 1, here you are interested in electric field here, and then there's 2 charges. Again, electric field due to negative charge is to the charge, toward negative charge. Electric field due to this proton is away from it. So the electric field here and here kind of cancel. But now, how about here? Electric field due to this proton is away, and electric field due to this electron is toward that electron. So then again, kind of cancel out. But now, electric field due to this two protons is away from the charges. So one and then the other one. So you gotta add these two vectors. And then how about here? One to the toward it, the other one toward it as well. So then you see electric field number 4 is exactly 0. So we have a 4 cases. Case number 1, case number 2, case number 3, and case number 4. Right? And the case number 4 is obviously 0. Right? So the A is not the answer. And then how about number 3? So repel, repel, right? In other words, away, away. So it's a left, right? They both have a left. And then how about, number 2? Electric field due to this proton is toward it, and then away from it, and the electric field due to this electron is toward it. But which one is greater? Of course, the plus sign has a greater electric field because this is a closure, right? So the answer is B, right? Pen, lighter, L, left hand, 0, right? And then similar question, all charges have an equal magnitude. Again, the same question. For example, number 4, what is the electric field here? Okay, toward. So cancel. So electric field here is gonna be 0. And then this is away from the positive charge, away from the positive charge, okay. And then how about this? Toward the negative charge, away from the positive charge. So two direction. So the electric field, each electric field, let's say, has the same direction. So you gotta add this. For number 2, electric field due to this electron is toward it. Electric field due to this proton is away from it. So this is you gotta subtract these two electric field, right? So the number 2 is least. And then now you gotta compare number 1 and 3, which one is greater, right? So the distance here, they have the same contribution, same distance. But this one also has the same contribution. But this one, the last one here, is the farther than this or any of this. So the effect of this charge is the minimum. So basically, number 1 has a stronger electric field. Right? So the answer is D, right? Number 1, strongest, D, least, and then number 4 is the 0 electric field, right? And then what is the electric field at the dot? Again, electric field due to negative charge is toward the source charge, negative source charge. So the answer is B. And now, electric field of multiple charges. So then now let's assume you have more than one charges generate electric field. Again, electric field is a vectors. So you have to add more than 2 vectors if you have multiple charges. Okay, so simply in a vector sum of electric field due to each of our charges. So for example, you have a dipole whose charges are 1.5 nanocoulomb for each, of course, has a positive and negative charges. And then this is separated by 1.2 centimeter. As shown in this figure, what is the electric field strength along the line connecting the charges at point 1.2 centimeter to the right of the positive charge, right here. Again, you have 2 electric force field. The first electric field is due to this proton. That's the direction is to the right, because away from the positive charge. And the second electric field is due to this electron that is toward the electric field. So the first electric field is a positive because it's to the right. And the second electric field is a left because it's a negative. And then what is the magnitude of the first electric field? For example, let's say this is a E1 positive, which is a K times Q is 1.5 nanocoulomb divided by R is a 1.2 centimeter, so 0.012 meter square. And the second one's same, right? Again, K times Q is a 1.5 nanocoulomb divided by R for this case is a 2.4 centimeter, which is a 0.024 centimeter, right? So then now if I show you the calculation, this is a E1, again, K times a Q1, 1.5 times 10 to negative 9, and then 0.012 centimeter or meter square. This is a positive because the E plus is a due to this proton, and then it's away from the proton. And the second one is to the left, whose magnitude is the same, except the distance is 2 times. And then if you calculate it, this is gonna be your answer. Of course, the answer will be positive because E plus is greater than E minus. So what is the direction of the electric field at the dot? Again, electric field here due to this proton is away from the proton. So this is going to be electric field due to this proton. And then what is the electric field due to the electron? It's toward it, right? So this is a vector sum of these two vectors. So your net electric field is to the right. Answer is D. And then similar thing, what is the electric field at the dot? This is almost exactly the same examples that we actually solved, right? Due to this proton, electric field is away from the proton, so to the right. And then due to this electron, your electric field is to the left. So then you have to subtract these two vectors, but now question is which one is stronger? Of course, the negative one is stronger because the distance is closer. So the answer is B. Okay. And the similar thing, you have let's assume you're looking for the electric field of the dipole. And for example, you're looking for electric field right here. This is exactly the same as the previous example, right? Your electric field here due to this proton, away from the proton, and then the second one is toward it. But again, this proton is a closure, so the net electric field is upward. And how about this point? Electric field due to this proton is away from the proton, and this is toward it. So the net electric field is a vector sum of this one, which is downward. So then now you can draw any electric field by this dipole moment, right? For example, here we found, right? You can choose any random position to find the electric field. For example, here, what do we do your electric field? Due to this proton, the electric field due to this proton is outward. So if you draw it carefully, this is gonna be this. But due to this electron, electric field is toward it. There's something like this. So the vector sum is gonna be this. Right? This makes sense, right? How about the electric field here, for example? This one, boom, here, right? And then this one toward it, boom. So the net electric field is down. So you can test, anywhere you see that's a vector sum of them. And then electric field, sometimes your electric field line is drawn with this kind of a curve. And then again, you have to remember two things, right? Electric field, the magnitude, and the direction. Electric field density will give you the strength of the electric field. And then at each point, you can draw the tangent line. That's the direction of the electric field. So the electric field is stronger where the electric field vectors are longer, of course, right? Because here, this is longer, this is shorter. You can also find it based on the density of it, right? In other words, where the electric field lines are closer together. And then the direction is the electric field vector is a tangent to the electric field line at that point. Again, you see this is straight line, and if you choose any random position, tangent itself is this line. So electric field is always along this line for this case. But your field here is stronger than here, right? Because you have a denser electric field line. So another rule is field lines cannot cross. This makes sense. Why? If two field line is closed, and then at that point, there's no way you can determine the direction because basically you have a two tangent line, right? That doesn't make sense, right? And again, this is a electric field line version compared to this is actual electric field at each point, right? So if you draw the more lines, small electric field lines here, and then you will at the end reach here. But basically, this is nothing but this picture saying. For example, if you are interested in electric field here, then again, it's a vector sum. Okay, plus charge outward, negative charge inward. So the net electric field is down, right? So this is exactly what you see from this example. Okay? So then now electric field line is drawn at which point electric field is greatest. How do you know that? You have to check the density of the area. Right? You see A has a strongest electric field there. And then two protons are in electric field. Which proton has a stronger acceleration? So stronger acceleration, larger acceleration. In order to have a larger acceleration, what do you need? You need a larger force, right? So this question is simply which one has a stronger electric force. So your electric force is given by Q times E, right? So they have the same Q. So that this question is simply which one has a stronger electric field. Of course, A, right? Line is the answer. So the answer is A. So which one will be two positive charges? For example, electric field due to proton is always outward. But if this is true, this doesn't make sense. Why? If the field line is toward this proton, this doesn't make sense as well. Why? This field line is toward this proton. This doesn't make sense, right? So your answer must be C or D. Again, D doesn't make sense. Field line is toward it, but this is the only field line whose electric field line is outward from the proton. Okay? So the answer is C. An electron is at the plane. You have an electron. What is the directional electric force on the electron? So you have a electron here. Be careful. Now you are looking for the electric force acting on the electron. So the force due to this proton and electron is attractive force. So your force will be toward it. And then this force repulsive, right? So the net force will be 8. Right? Okay, but I can change the question. Let me change the question. So if we are looking for, this is an interesting question. If we are looking for electric field instead of electric force, what would be the answer? What is the direction of the electric field right here? We assume electric electron is located here, right? Electric field, again, the important concept here, your electric field does not depend on the test charge. So you forget about electron here. You only care the location. Electric field due to this proton is outward. Electric field due to this electron is inward. So the net electric field is downward. Make sure that you understand these differences. Okay, again, electric field does not depend on the test charge, for this case, the electron. Okay, good. Let me know if you have any question. You can send me, please send me an email. Thank you.